Yeah, so we said we have linear motion. Everything that we talked about in linear motion has a twin in circular motion. This is what we said. Yeah, so we said acceleration is going to be angular acceleration represented by alpha. This is measured in meters per second squared. This is radians per second squared. This is meters. We said this, that's what we had. Then the only thing which will be consistent, displacement will be represented by theta. That's what we said. This is just like theta from your trig, just this guy. And the units here is just radians or revolutions sometimes. And this is to initial velocity, which is omega initial. The only thing that is going to be the same in between these two types of motions is the time. The time is still going to be in seconds. And the equations that make these guys to be connected as follows. We say the linear acceleration is equal to the angular acceleration times r. And we also said linear velocity is equal to angular velocity times the radius. Then also the linear displacement is equal to r times the angular displacement. These are the three relations, how these two types of motions are related. These are the only things that can join us or help us to move from something moving in a circular path. We are saying anything moving in a circular path has the ability to actually stop moving in a circular path and then just move straight. That's the reason why we have accidents. For example, if you are learning how to drive along, let's say, the roundabout, there's a way that you are supposed to drive and reach the roundabout to avoid accidents, and the car or the device that you are rotating around this particular circle to move away from the circular path. So yeah, we have that type of, it's possible to move from linear to circular. That's what we're basically saying. And we ended on the notation. So we ended on the conversion, the conversions that we did. We just said we know to say 1 revolution is always going to be the same as 360. Now we know to say 360 is a little bit big, so we prefer to be using radians, because from trigonometry we said angles can either be measured in what? In degrees or radians. So we're just going to stick with it. 1 revolution is equal to 2 pi radians. That's what you have. And I gave us examples. If you have, let's say, 20 revolutions per minute, so this is written as 20 rpm. This means revolutions per minute. We can convert this. This is the same as revolutions per minute. We want it to be put in radians per second. So this will be 20 revolutions over a minute. We'll just multiply this by 2 pi radians. And over 1 revolution times 1 minute over 60 seconds. And I should have mentioned here to say some calculators will be giving you wrong things. You have to convert you have to change the mode of your calculator to radians. That's when you get the right thing. So on the calculator, if you're using Casio, for example, there's a part where there's mode. You click there twice. The first time you click, there'll be something like comp, SD, reach. Then click there again, you get DEG, then rad, then gra. So you select to put your calculator in radians. Then you work out everything. This is going to be the case whenever you're dealing with radians. Now, the common mistake people make is after converting or rather changing their calculator to radians and they're working questions on circular motion, they forget to turn it back whenever they go back to other questions from other topics. So you notice that if your calculator is in radians and you try to punch cos 20 on the calculator, it will give you something like a 0.4. Then if you take it back in degrees, which is 1, you try to punch the same cos 20, it will give you 0.9. So you notice there's going to be a difference. So your answers can be affected. We only put the calculator in radians if you are dealing with it. Circular motion, that's the only thing that we do. Is that okay? True. So here we cancel our minute, the revolution also cancels. Then you punch everything here. So this is going to be, we put our calculator in, and put it in radians. So we're having 20 times 2 is 20 times 2 pi, then divided by 60. Here we got something like a 2.09 radians per second. So this is how you convert from revolutions per minute to radians per second. This is what we did yesterday. This is where we ended from, right? So now we're going to just continue and give us do an example. So I'm going to show you examples on how we can apply what we've learned here. Okay, so let's call this guy here to be our example 1. This is what you have. They are saying an electric fan is turned off and its angular velocity decreases from 500 revolutions per minute to 200 revolutions per minute in 4 seconds. Question 1, they want us to get the angular acceleration in radians per second. Then they want us to get the angular displacement in radians after the 4 seconds. And how long it takes the fan for the fan to come to rest. So these are the questions that we are given. So let me just do the data collection here. Yeah, so this is what they have given us from the question. Then they want us, the first thing they want us to get is angular acceleration. That's what they want. Then the second one, they want us to get angular displacement. And then the last one, they want us to get the time it's going to take for it to come to rest, meaning now we're starting from, we can just say we're starting from the 500, and we're starting from 500, and the final is going to be 0 in this case. This is per minute. The final velocity is 0 revolutions per watt per minute. So what is going to be the time? That's what they want on number 3, the last part. So all the equations that you learned in linear motion are going to be changed. So like the equation that you learned to say acceleration is equal to v, then you say u, then over t. We're just going to change this. This is the same as alpha is equal to, we just use the letters in circular motion. That's basically what we have, then over t. And you know to say we cannot use these guys, the revolutions per minute. We have to convert each one of them to radians per second. Okay, so you're saying this one here is 52.398. Okay, this is in radians per second. Then the 200 is going to be what? Okay, so you're saying this is 20.94 radians per second. So if you have these two in proper units, meaning we can just use our equation now directly. So on the units, we have to indicate them so that we show that this is actually going to be radians per second squared. So this is radians minus the final minus the initial, right? So this is 52. Expect acceleration to be negative because this thing was slowing down. Then here we divide by our 4 seconds. Time is still going to be the same. So if you punch this, alpha is equal to negative what? Negative 7.8989. This is radians per second squared. So we have our acceleration, which is negative. Then the second part, they wanted the angular displacement, right? The length. So this is going to be the same equation. How is the equation for distance? Remember we say distance, or S, is equal to, we used to say initial velocity. This is what you used to say. So just replace with the twins now, the letters. X we said is this. Here we put omega initial. Time will still be the same. Then we have alpha, then t squared. The initial is simply 52.35. That was in radians. The time is 4 plus half. The acceleration is negative 7.8585, is it? Then this is 4 squared. So if we punch everything here, what do we get? Yeah, okay. So it's 146.6. This is radians. You can put it in radians. Or you can convert this to revolutions. If you put it in revolutions, it's going to be what? You just divide this guy by 2 pi. It's going to give us 23, something like a 23.3 revolutions. It's just going to be in radians, or rather revolutions. Then the last one, they wanted us to get the time it takes for it to go to rest. So meaning, if we're looking for time, we already know to say, how can we do this? They're saying, let's see the question. They're saying, how long it takes the fan to come to rest, right? That's what we're saying. So the acceleration is still going to be the same over this period of time. So if we're looking for, saying how long, meaning final velocity is 0, final velocity is 0, then the initial velocity is what, 52.35, then plus, then we are having the acceleration to be negative 7.85, then the time is what we're in need of. So you can get the time here. So you take this side, 52.35 is equal to negative 7.8585, then there's a t. Yeah, so we divide with this 5. Yeah, so t is equal to 6. Yeah, so 6, something like a 6 seconds. Yeah, so that's basically how you do such equation. So they are the same with, it's the same thing. The equations are all going to be the same. We're just going to be using different letters now. So this gave us t is equal to 6 seconds approximately. So all the equations you learned have twins. So now you should be familiar, or rather you should get used to solving using these guys here. So you should be thinking in terms of this now. Yeah, then you know this is equal to what? U. So this is okay. This part is okay, right? For applying these equations, isn't it? Okay, so now the next part that I'm going to talk about has to do with strictly something moving in a circular path. Already, this is already in a circular path. Everything is swinging. I mean, is rotating. But we specifically want to talk about what we call centripetal. So centripetal acceleration and force. So now, if something is moving in a circular path, what we are basically going to say is that the way that this object moving in a circular path feels is that it's going to be having different components in terms of x and y as it is moving around this circular path. And it wants, the normal tendency, what it feels at most is that it wants to move towards the center. Right? Have you ever done or used a brazier, then you swing it using your hand, like try to bebe shambala, like you know how those people do it, like, right? The way the hand feels, like it's like the brazier wants to fall on you. So like there's a way that you're going to feel when the brazier is on top of your head, as if it just wants to fall. So anything moving in a circular path, it has a tendency of wanting to gravitate towards the center. And you know, to say from the center to any of these guys, the distance is the radius, right? From the center. So the feeling or that acceleration that wants to pull any particular object moving in a circular path towards the center is simply what we call centripetal acceleration, and it's given by the following formula. This is the formula that we have. The first version of the formula is that the linear velocity that it can have, if it was to move in a linear velocity, I mean in a linear direction, squared divided by the radius. This is the basic formula for centripetal. We put a C down to show that this is centripetal acceleration, and it's simply allowing us to say anything moving in a circular path has a chance. If you let go of it, it will move in a linear path. That's what we mean by centripetal, this guy. And it mostly just wants to gravitate towards the center. So this is the formula. Now, since you remember we said V is the same as omega and R, one of the relations between linear and circular. You remember this, right? So where there's V squared here, we can replace with omega and R. So centripetal acceleration can be redefined. We can put omega and R, then square it. There's an R down. This is just going to be the same as omega squared and R squared over an R. This is our AC. You see that one R and one R can cancel, meaning we have another version of the centripetal acceleration, which is just omega squared, and is when you have angular velocity, when you have omega, you can use it also to get centripetal acceleration. Is this okay? Okay, so apart from this, apart from what we've done here, we can also say if there's acceleration, meaning you know there should be force somewhere, right? So the force that causes centripetal acceleration is called centripetal force, and it's given by this. Now, because you have two versions of centripetal acceleration, you have this version and also this version, meaning even force is also, centripetal force is also going to be having two versions depending on the expression for centripetal acceleration that you are using. So centripetal force can just be, centripetal force can be Fc is equal to m, then we put this guy if you're using this guy here, or centripetal force can be the mass and omega squared and r. It just depends on the acceleration that you've decided to use. Yes, yes, we can use that one, yes. Yeah. But then if that one is just if you're trying to convert between linear and secular, but the actual formula here should be this one. If you want to get, or rather use, centripetal acceleration, these are the actual formulas on how we get it. So that equation is just if you want to convert. If I give you, for example, if I give you angular acceleration, then I want you to get the linear version. You just multiply it by the radius, it will give you this guy. So this is just to move back and forth between the linear motion and circular motion. But then this one is strictly the acceleration that wants something to gravitate towards the center. That's the centripetal acceleration. You notice here there's a C as a subscript. Here there's no C, right? Yeah, so here a little bit of formulas, they're going to pile up a bit, but they're just going to still be simple. You can actually derive them, in short. That's what we're basically saying. So we've only talked about centripetal acceleration, which has these two formulas, giving us two versions as well of centripetal force. The force that is going to cause the centripetal acceleration, that's basically anything that causes, if there's a circular thing, if something is in a circular path, there's radius here, right? What the centripetal force does is to maintain the distance between the central part of your circular path, like the circle. The reason why these guys are not going to move is because in as much as there's weight, so let's say if it's a car, right? Imagine this is a car at a roundabout. So we believe that the reason why the car has weight and everything. Imagine it's swinging. This thing is hanging in the air. This thing is it wants to gravitate towards the center. This thing has weight, but we're saying in this case, centripetal force will be acting in the opposite direction. These guys always want to move towards the center, but they don't end up moving. Why? Because centripetal force keeps them at r distance from the center to maintain the circular motion. That's basically what centripetal force does. So there are arguments to say centripetal force can either face towards the center or away from the center. If we're talking about, there's a case we're going to be dealing with. If there's a car at a roundabout, this thing wants to move towards the center, right, by the force of centripetal force. But then there's friction. Friction is going to keep it away from moving towards the center. So the forces will be balanced. We'll say this is just equal to friction. So Newton's laws, yes, the friction formula is still going to be the same. The mu and mg, that thing, right? The normal force times, yeah, so it's still the same. Yeah, so maybe enough of this. Let me show you how we can apply this. Maybe you make sense out of the following example. We're going to call this guy to be our example 2. I just want you to see the application of centripetal force. So we're saying, consider the conical pendulum shown below, in which a bulb of mass m tied to a string of length L moves in a circular path of radius r. Sketch the forces acting on it in a free body diagram. Obtain the expression for the final velocity, which is v. That's what we need. So firstly, I want you to be reminded that centripetal force that we're going to be in need of is simply this one. That's the one that we'll consider the most, because centripetal acceleration is v squared over r. And according to this, so with what you've been given here, we can assume that there is tension in this string. Obviously there's going to be tension in this string because it's holding this guy here, right? So we're going to resolve with respect to this angle here. Look at where the angle is. The angle is just directly here. So we're going to resolve, if you make this guy here to be your y-axis and you make this guy here to be your x-axis. So you're going to get t sine theta, and you're also going to get t cos theta facing down. This is with respect to our tension. So I've just resolved the tension, meaning there is, I'm just going to draw a free body diagram. There's t sine theta, then there is t cos theta facing down, the tension in the string. This is t cos theta. That's the first, these are the first two forces that we can identify. So we have used the tension in the string. Then apart from that, you're also able to tell from here, according to this, you know, this is height, this is h, this side, right? This is h. So you can also tell that you can have what, or rather you can just use the theta and this guy here, you know, to say sine what? Sine theta is the same as r over L, right? So meaning L is just the same as, or how can we say it? R, the formula for R is the same as L, then sine theta, so we can keep this as well after using the SOHCAHTOA. Then if this thing is swinging in a circular path, so the next force that you can think about is centripetal force, which is trying to pull it towards the center, which is Fc, which is this guy that we've said, that's centripetal force. So the only forces that we can see here are these three. So let me just write them properly. There's 3 cos theta. And this thing here has weight. This guy has weight. So the weight is equal to mg. So now the reason why we're going to flip this guy here, because the bob is not cutting, it's not going to be let go, right? So meaning the x component, actually the x component of our tension, this guy here, is actually opposite from the weight. So this is actually going to face up. So we change it, we make it face up. And then we have the other one here. Remember we had t sine theta that was going out. Then we have Fc, which is going in. So these are the 4 forces that are always going to be acting on a pendulum with the bob swinging in a circular path. They will never change. That's a good part. They will never change. They will always be like this. In short, all I'm saying is that you're going to equate, because everything is balanced. This thing is not cutting or anything. So it's going to continuously move in a circular path, meaning the forces are balanced. We're just saying t sine theta is equal to the centripetal force, which you know the centripetal force to be mass v squared over r, and then the other one will be t cos theta, which is just going to be equal to the mg. That's what you have. So these are the 2 equations that you'll always be having. Is this okay here? You can phrase the question is, they will put the theta here at this particular point. So when they put the theta here, just subtract that angle given by 90, then you get back your theta, which is here. You continue with your working the way we've done it here. Is that okay? Okay, yeah, so that's what we basically have. So these equations are always going to be fixed. And from here, we're just looking for the expression, by the way, right? They're saying sketch the forces acting on this, obtain the expression for the final velocity v. So which equation between these two has final velocity? So to make life easy for us, because we don't have tension and we don't have any value here that we can think of, that we can use, we divide. You've done trigonometry now. You divide the 2 equations. You know, to say if I divide this and this, I'm going to get the tan. I mean the tension, the t cancels. Sine over cos is going to be tan, right? Then is equal to, we are dividing the mass and velocity squared over r divided by mg. Then you're saying the tan theta is equal to, here you notice that there's a 1 this side, meaning this is going to be mv squared r, 1 over mg. The mass can cancel. This is tan theta is equal to v squared over rg. Then this will cross multiply, meaning this is going to be v squared is equal to rg with a tan of theta, then square root. So this is the expression for the velocity with which this thing is swinging with. So this is the expression that they wanted, the simplified version of the expression. This is okay? Okay, so if this here is okay, look at the next example here that we're going to do, example 3, which has values now. So from here, they're saying calculate the angular what? The angular speed in radians per what? Per second. So a small sphere, the mass has been given. This is what you're having. Then they're saying it's suspended by a string. This is what you have along. So this is, you're given what? By the length of the string is what? 50, right? 50 centimeters. This is the same as 0.5, isn't it? Meters, right? The radius is 25, which is the same as 0.25, right? The angle is not given, so we can use our knowledge for SOHCAHTOA for the trig to get our angle. So this is just going to be sine what? Sine theta is equal to opposite over hypotenuse. Opposite is 0.25. Then this is just 0.5. So theta is equal to what? Sine inverse of 0.25 over 0.5. Then theta is equal to, we already have an expression, we got it previously. We say the velocity is just the same as the radius, g, then tan, the theta. So this is just going to be square root, the radius is 0.25, then times 9.8, then times tan 30, the square root. Here we'll get v, right? So what are you going to get as your v? Is what you find here, since this expression is what we're using to get our velocity from the previous example 2, you get this velocity here. They're asking for the angular speed. They want omega. So meaning, you not say v is related with omega like this. The v is 1.189. We're looking for omega. The radius is 0.25. So divide both sides by 0.25. Even this side by 0.25. So your omega, which is your angular speed, is going to be what? 4.75. 4.75. This is radians per second. So this is the 4.75. So this is what they needed. This is how we always tackle a question that has to do with a swinging pendulum in a circular path. And you notice that tension will never be, if it's given, meaning you have to resolve it. But if it's not given, you opt for this previous formula that we solved for the expression for V, which doesn't include tension. It cancels out tension, right? So that's basically what you do. Is it a little bit too much? Is it okay? Yeah, so this is basically the first application you have for circular motion. This is the most simplest type of application that you can have. Yeah, so another thing I may just add based on what we're going to do next. So circular motion, what we've done here is just like a simpler version of what is ahead. So this is just like phase 1, and the next part that we're going to do now is what we're going to be calling rotational motion. It's like the advanced version. It's the same thing, but a little bit advanced. And I'll just like to give you a heads up on what we are going to look at. So far, we've just talked about the following equations that you have to master. I won't give you the ones that you know, like this here, to say the ones that you just have to flip and replace with the letter. So these, the motions ones, I won't write them. The motions ones are obvious. But the only new thing that we've added today, as of today, we've just said centripetal acceleration is v squared of this, or this is an error here, sorry. There's an error down. Or we can have centripetal force is omega squared and error. Meaning, even the centripetal force can also give us two versions, right? We can have this one, or we can have the centripetal force that simply looks like this. So these are the two equations that the two sets of equations we've talked about. And the next thing that we're going to add on here, that I'm going to add on, is what you call, is it gravitational force? So let me just say gravitational force between two particular objects. So the third equation that I'm going to give you is F is equal to G, M1, then M2, over r squared. If you are comparing two particular objects, we're saying everything, if you put two objects close to each other, there's always going to be some form of attraction between them. And this is g, this is a constant, this is something like a 6.6 times 10 to the power negative, I think 34 or something, joules kilo. They always give you the capital letter G. This is the mass for the first object, mass 1. This is the mass for the second object, that's mass 2. Then the radius is simply the distance from the central part of this object to the central part of the other object. That's basically what you call the R. Yeah. Or some, is it? It's actually here. Point of correction. The central. So between the two, there's one which is swinging around the other one. So it's between the central part of one of the objects to the outer surface of one. Yes, that's how we measure the speed of the Earth, because we take the galaxy to be like, to have a central part where all the planets are going to be revolving around the sun. So this particular formula is used to calculate the force of attraction between satellites. That's how they're able to calculate the speed of, let's say, a falling star or something, those things in the galaxy and everything else. This is mostly an application for satellites. That's what we're going to be doing. So this will be the next part that we're going to look at, and also we'll talk about torque and everything else. But for today, hope you're okay with centripetal force and centripetal acceleration. This is okay, right? Okay, so if this is okay, then we can end here for today for physics.